chain that is interacting with an interface. And the situation we'll be looking at is that there is a polymer chain living in the neighborhood of this interface, and each time it hits this interface, it picks up a reward. So it gets a negative energy for every intersection with the interface. And so it will be interesting, it will be favorable for this polymer to be in the neighborhood of this interface. And we will be asking the question, is the interaction strong enough for this polymer to actually stay in the vicinity of this interface and try to hit it many times? This is a phase that we would call a localized phase. Or can it be that the interaction is not strong enough, and that even though the polymer gets a reward when it hits the interface, the reward is not good enough for it to stay in the vicinity of the interface, and therefore it would basically largely ignore the presence of this interface. And such a situation we would refer to as a delocalized phase. And we will be trying to describe when it is that these two phases occur, and we want to prove that there are indeed two such phases. And then we will try to say something about what the polymer is precisely doing in each of these two phases. And there will be two parts to the talk. Actually, there will be three parts. The first part, I will be talking about a version where the polymer can live on both sides of the interface, and it can hit the interface coming from both sides. This is what we refer to as pinning by an interface. And I will also be looking at a one-sided version where the polymer can only live on one side of the interface. It cannot go to the other. So now the interface is like a hard wall. And then that version is called wetting. So I will come back to that distinction as we go along. And then in the third part of the talk, I will be asking a question of the following type. If I start to pull on a polymer that is adsorbed at an interface, what force do I have to apply to pull it off the interface? So in the localized phase, when the polymer wants to really stick to this interface because the reward is good enough, how much do I have to pull it off the interface? And we will see that something very interesting is happening there. There will be a rather unexpected phase diagram as a function of the force, which is called a reentrant phase diagram, and it's a bit delicate, and we will come to that point when we get there. I will come to that. Okay. So there will be two versions. There will be a version of the polymer, and I'll start to write down some formulas in a second. The pinning version. So this would be the two-sided version, and there will be a wetting version, which is a one-sided version. So we will be looking at both cases, and this is a situation where you have your interface and your polymer can do either of two different things. It can either sort of basically ignore the interface and not spend much time close to it. This would be called the delocalized behavior. And it can also be in a situation where it sort of wiggles around the interface, making many intersections because the reward is very high, and here it would only make a few intersections and then basically sort of wander off away from the interface, and this would be the localized phase. And the polymer can live on both sides of the interface in this, what is called pinning version. And the wetting version is just a variation of this two, where you say, well, the polymer is not allowed to go below the interface. So it cannot, so this is a forbidden region. It cannot go there. And in this case, the delocalized regime would be that you sort of touch the interface a few times and then you go off to infinity. So this is the delocalized phase. And here you would have a phase where you try to sort of touch the interface many, many times. But always staying on one side of the interface. And this would be the localized phase. So we're going to talk about two phases in two different versions of the model. And the name pinning is quite clear that you're trying to be pinned by an interface. This wetting name comes about because you can think of these things as sort of, these excursions as sort of droplets that are lying on top of an interface, and therefore this phase means that you are sort of wetting your interface with droplets. And that's where the name came from in the physics literature, and I'm using it here, but you do not need to sort of give that any particular meaning. Okay, so that's what we're going to do. Now, a nice thing about this model is that it is simple enough to be able to do all sorts of detailed calculations. And we should enjoy that, because it's not very frequently that you can do complete detailed calculations. When for lectures 4 to 6 we'll be talking about polymer models with disorder, and then life is getting more complicated. Don't worry, I've promised that every single lecture is going to be independent of the other one. So, but this is a nice model. Let's spend some time to see what we can do. So, I have already shown that picture. So let's go to the pinning version of the model. And for the pinning version of the model, so we're first going to look at this example 1. Okay. If you want to define a model, remember you need to specify the set of paths that you are allowing, and you need to specify an interaction Hamiltonian. Those are the two main ingredients of your model, and then you get a Gibbs measure, and that is describing your random polymer. So for the pinning version, so this is the first model, we're going to look at a set of paths that is the set of all directed paths. So it's so let me write that down. So we're going to look at the pinning model now, and our set of paths is the set of all n-step directed paths, okay, with arbitrary vertical increments. So it's all sequences of paths where now I add the time index here. So if I increases, the time index is also increasing. So the presence of this I brings us into a directed path. So each time time increases, time goes up, and then you can make an increment that is completely arbitrary. It doesn't have to be nearest neighbor. We will in fact be looking at a much larger class than nearest neighbor paths. If it would be nearest neighbor, it would mean that you would go to the right and up, so northeast or north-south. But here you're able to make more general increments. I'll draw a picture of this path in a second. And then with every such path, we are going to associate an energy, which is given by our Hamiltonian, and it will be minus a parameter zeta, which can still be arbitrary, but our main interest will be in positive zetas, times the local time at the interface. So how much time does the path actually spend at the interface? So the Hamiltonian here which depends on a parameter is minus zeta times ln w, and this is the local time of w at the interface. Okay, so each time I hit the interface, I get a negative energy minus zeta. And so if zeta is positive, this means that the path gets rewarded under the Gibbs measure when it hits the interface. And if zeta would be taken negative, it would mean that it receives a penalty. And the Gibbs measure, as always, once you have specified these two ingredients, there will be a Gibbs measure. Every path gets a weight that is the exponential of minus the Hamiltonian of W for every path in the set of allowed path. And so this is the measure that describes the random configuration of your path. Yeah, in principle, I'm allowing all sorts of jumps. Yeah, and I'm going to soon put, thank you very much. That was very important. I forgot something here. It's on the next slide. I'm going to put here P and W. Thank you, Pablo. And where this is this is the law on Wn of a reference random walk, right? And I'm going to choose that reference walk in a second. Yeah, that was very, very important. So here's the Gibbs measure again, and I'm going to compare the polymer with interaction with an arbitrary random walk that takes care of the vertical motion. It doesn't have to be simple random walk. It can be done much more generally in this model because it's so simple that we can do explicit computations. And so this Pn will be the description of some random walk near to this interface if it's not interacting with the interface at all. And this factor here is giving the tilting due to the interaction with the interface. And for this Pn, we can take essentially an arbitrary directed irreducible random walk, and we will make some assumptions about it, but it can be quite general. It doesn't have to be simple random walk. So what this does is that it models this polymer with a reward or a penalty. So here is a picture of a possible path in my path space. So suppose I take a 7-step path. It can sort of make arbitrary jumps. It doesn't have to be nearest neighbor. And you see where it goes, and you count how many times it hits the interface. This particular 7-step walk hits the interface 2 times. I do not count the initial hit of the interface at time 0. You could, but that's just a choice. And so you can look at any arbitrary path here without the interaction. So if you put zeta is equal to 0, it would just be given by the law of some arbitrary random walk that always goes 1 unit to the right, but whose vertical increment can be anything you would like to choose. And with the interaction, it is tilted according to that Gibbs measure. Okay, so that is the setup that we are looking at. And one could take the vertical motion to be that of simple random walk. That's certainly an interesting case, but we will be able to go much beyond that. Now, in order to understand this model, it is clear that already, you know, even before you start thinking about this in great detail, that what will be important for us to be able to do is to understand the excursions of the path away from the interface. So this path walks around in space until it hits the interface. And only when it hits the interface will it pick up a reward. And then it moves away from the interface, nothing happens, no contribution to the energy until it again hits the interface, and then again I pick up a reward. So if I am able to understand the distribution of the excursions away from the interface of my reference random walk, the random walk that does not interact with the interface, then that should be the ingredient on which I can start to build the analysis of the model with interaction, because the interaction is only happening at the end of every single excursion away from the interface, and it picks up a simple factor. So somehow we should be able to, if we accumulate knowledge about the excursions of the reference random walk away from the interface, we should be able to make progress on understanding this model. And so let's look at that first. So we are going to take our reference walk. It's this reference walk here that doesn't interact with the interface. And let's introduce a quantity R of n, which is the probability that you will make an excursion of exactly length n. So this is the probability that you will not hit the interface at any time from time 1 until time n minus 1, and then you hit the interface. So it is going to be, so let me write that down. Rn is the probability under the reference random walk to make an excursion of exactly length n. And n can be any number from 0. Don't confuse this n with the length of the polymer. Maybe I should have called it m, but I chose to pick it m. So it's the probability that you will return to n at time n. But you may also do something like, you know, jump over it, and so it is in this model allowed to jump over the interface. I'm only asking what is the probability that you will be precisely at the interface again for the first time at time n. And this is a quantity that is a key quantity. We're going to make an assumption, key assumption. We're going to assume that this Rn is of the form n some slowly varying function times divided by 1 to n to the 1 plus a, where for r n going to infinity, r is slowly varying, so it's something like for instance a logarithm or power of a logarithm, and we will want to take alpha a number that can be any exponent between 0 and infinity. The case 0 is a bit, we can still sort of add that, but yeah, well here I actually kicked it out, but so let's do that too. Let's not worry about the case 0. It's a kind of boundary case, so let's not do that. Okay, and if you want to take simple random walk corresponds to A is a half and L dot constant. So this will be a good special case to keep in mind, but we can be much more general. So if you would allow more general random walks, you can play with getting different exponents A, different slowly varying functions. And so this is the only input that we will need. So this assumption will be the only assumption through which our reference random walk plays a role. Yes?
What is the physical significance of the model in which the random walk is not irrespective?
Well, you can think of a polymer chain whose monomers are not always of the same length.
Yes, but in the event when it jumps across the interface,
Yeah.
so it's straightforward.
Yeah, so yeah, you could say if so this would be a situation where a monomer could sort of jump over an interface and not seeing it. So if it would be very long, maybe if the interface is very thin, it would have a very weak interaction with it, and we are going to ignore that. Now, on Monday evening, Yuval Perez said, the purpose of reality is to provide, to inspire good theories. So let's keep that in mind. But it's that's a good remark. Okay, now, so I said the only thing that we really need to know about our reference walk is this behavior. That's our input, and it will only manifest itself through this function Rn. Okay, so here is the, let's see, why is it? Okay, so I will have to go on manually. So here's our first theorem. We can compute for this model the free energy completely explicitly. And what you do is the following. You build a generating function out of these first return time probability distribution. So remember, this is a probability distribution on the positive integers. And so it's, when you sum over n, it sums up to 1, because we've assumed that our random walk is recurrent. You can get rid of that assumption, but we're not going to do that in this lecture. And you build your generating function out of these numbers. And then once you have this generating function, there's a little bit clash of notation. Here I'm using the R for n, and here also the R for with an x, because you can almost, maybe I should have put a bar or a twiddle over it. Sorry, I didn't do that. And then the free energy, which is always the key object to understand the phase transitions, is a it's the solution of something very simple. If zeta is smaller than or equal to 0, then the free energy is 0. And if zeta starts to become positive, so this means you are really getting a reward when you hit the interface, then it's going to be a function of zeta that is the solution of this very simple equation. You take e to the minus zeta, which for positive zeta is a number smaller than 1, and you look for the value of r such that if x is e to the minus r, that would make this generating function at that point equal to e to the minus zeta. And if you find that r, which is unique, then that's the r that is your free energy. So, message, it's very simple here to compute the free energy, and you get it from just knowing the generating function of the return times. So let's do, this is dead, I'm afraid. So I'm really going to have to put it here. And so let's give a proof of this very simple theorem. Let's spend some time on it. First thing that we're going to do is prove that the free energy is 0 when zeta is non-negative. Well, that's not very hard. If zeta is negative, so let me remind you what Zn is. So Zn of zeta is the sum over all paths in your space of e to the zeta times this local time. And if zeta is smaller than times p, and I keep on forgetting that, times the measure on your reference random walk. Now, if zeta is smaller than 0, this exponential is smaller than 1, and therefore the free energy, the partition sum is smaller than or equal to 1. On the other hand, it can be bounded below by saying, let's look at a path that up to time m does not intersect the interface. Then I will get a lower bound. I just pick the set of all paths that do not hit the interface up to time n at all. Okay. Then this local time will be 0 because I'm not hitting the interface at all. This factor will be 1, and I'm left with the probability of the reference path not hitting the interface up to time n, and that's the sum over all n larger than n of Rm. And since I am assuming that this Rn is decaying polynomially, the lower bound is polynomial in n, and therefore this partition sum is sandwiched between 1 and a polynomial, and therefore its exponential growth rate is 0. Okay? So the lower bound just comes from having a strategy where you say I'm not hitting the interface at all until time n. So very, very simple. Now, what happens when we take our positive? Well, to do the argument, then we are going to do a little trick. We're going to tilt the distribution in a certain way. What we're going to take our original return time distribution, and we're going to tilt it by a factor e to the minus r zeta n, and we're going to multiply it by e to the zeta. Because of the definition of r zeta being the solution of r, the generating function at the point e to the minus r theta is being that. So if I now, because I've put the zeta here, this is again a probability distribution. It's a probability distribution that has an exponential tail, but it is normalized exactly because of the definition of r zeta. So I'm introducing a new object, and it's a tilted version of the original distribution. And because r zeta is positive when zeta is positive, this thing has an exponential tail, and so in particular it has a finite mean, irrespective of whether the r had a finite mean or not. This thing has a finite mean. So this is a tilted version. I'm going to use this tilted version. Let's see if this works again. I'm afraid it doesn't. So let's see what we can do with that. Well, let's first look at the partition sum, where I'm going to restrict the endpoint to be back at the interface. So let's define a partition sum which would be the same as the old partition sum, but forcing the path to be back at the interface at the end. So this is going to be a kind of auxiliary object, and as was already explained in the first tutorial by Nicolas, if you put such constraints at the very end, you cannot really change the free energy by much. I will mention that at the end. But let's first look if we can understand the exponential growth rate of that object. And the nice part about that object is that I can write down a formula for it in terms of this tilted distribution. There is something missing here. There should be is equal to n. I'm sorry about that part missing. So if you have constrained yourself to be at the interface at time n, then what you can do is you can make a number of excursions, and they can be sort of two-sided. They can even jump over the interface, but let's draw them like that. And these, we can split the sum into all the possible length of these intervals, and J1 up to Jm would then have to be n, because I know that I will be back at the interface for this auxiliary partition sum at the end. Now, each of these loops, each of the excursions will have a probability r to the ji, but when I replace the r by the r zeta, I'm tilting things, so I can take out this factor in front of here because I had put it in there for every single excursion. And then I would get a contribution at the end of every excursion of e to the zeta, but that was already in this quantity. So remember that in this quantity there was this factor in here, which I am now putting in and taking out, and this factor is exactly the factor that you would get as a reward for every self-intersection. So in the end, you wind up with this big sum, and it's a sum over all m, possible m, of all excursion length of this tilted distribution. And then you can express this partition sum here, the partition sum constrained to end at the interface, by this very simple factor times this sum. But this sum has an interpretation. This sum is exactly the probability that the random walk whose excursion distribution is given by r zeta instead of r is actually hitting the interface at time n. So if I take t to be the process of renewal times, as you could call them, so the times at which I hit the interface of this tilted random walk, then this sum is exactly the probability that that tilted random walk is going to hit the interface at time n, because here are the cost of the loops. I'm looking at all possible loop lengths. So this has an interpretation. It has the interpretation of the probability that some tilted random walk hits the interface at time n. Now, why is that important? That's important because there is a renewal theorem that says if this random walk has a finite mean, which it has because it has an exponential tail, then such a hitting probability will just go to 1 over the mean of the random walk. So this is the classical renewal theorem for in this case, applied to the excursions of a random walk. And so we know that this is tending to a constant. And therefore, we know that this term is completely harmless on the level of exponential. And therefore, the growth rate of this function here is exactly the arc-c, r zeta that we are after. Right? So you see that we have very strong control over this partition sum. We know that it is an exponential times a constant. And it is this very strong control that allows us, in fact, to say much more about this model than the things I'm telling you about now. Okay, then there's a final little step that you have to say, well, but you took here a partition sum restricted to path having to end at the interface, whereas originally you didn't have that. Well, as Nicolas explained in the first tutorial, that is a very simple thing to get rid of. The partition function without the end constraint can be sandwiched between the partition sum with the constraint is always smaller and the one, and it cannot be bigger than a constant times n times the constraint partition sum. So really, these two things are very close to each other, and therefore the growth rate cannot possibly be any different for the two, and therefore you do indeed arrive at the growth rate r zeta. Okay. So this was a very simple proof, and I wanted to spend some time on it because it conveys the message that you can do very precise calculations here. So let's look at some examples. Let's focus on the simple random walk. For the simple random walk, the generating function of the first return time distribution, so if I take this Rn, put it into a generating function, it has a very simple form. You can find this in many places. For instance, you could look at Spitzer's book, and this generating function is very simple. The free energy of the simple random walk interacting with the interface, therefore, since it's the solution of this equation, you can find the free energy, which is the solution of this equation here, to be given by this simple formula. So in that case, you get a closed form expression of your free energy. If you have some other nice random walks of which you can compute this, there are many, then you can still get a nice expression here. Okay, so we have, yep.
When you let the parameter a go to 0, it corresponds to two-dimensional random walk.
Yeah.
And you have a logarithmic
exactly.
part of it.
Yeah.
So you can still do the...
Yeah, you can still add a is equal to 0, and you can do all the computations. I just left it out here, but you can do that. And for instance, if you would be thinking of two-dimensional simple random walk that is not interacting with a line but with a plane, right? Then you still have an Rn, and the Rn would have exponent 0 indeed. And I can take a three-dimensional walk, and then the exponent can be, d-dimensional can be d over 2. There are many things you can play with here. So I'm really only focusing on the most simple example. But this can be completely carried through. So this free energy, if you plot it, looks like that. It's 0 for negative zeta, and it has a curve that goes up like this, and it's asymptotic to this linear line. So indeed, we see that the free energy has a crossover at zeta is equal to 0, and therefore at this point, the model has a phase transition. The moment you start to switch on a positive interaction, you will see that the reward is apparently good enough for the polymer to want to sort of stick to the interface and thereby being able to pick up many rewards. Yeah?
The Gibbs measure, you have a Markov representation in this case of the Gibbs measure.
Yeah.
Also in the other case, for any random walk, you have that?
Yeah, because I'm only, nothing happens until I again hit the interface and everything starts again. So I can decompose the whole problem into counting excursions. So when you go to the excursion language, everything becomes Markovian.
Doesn't even need to be a random walk.
Doesn't even need to be a random walk. Right. So it can be anything. So I start from a random walk, but if I would pick anything else than a random walk, I would still be able to do this. Okay, now the derivative of this function looks like this. And the derivative of the free energy is important because, as I explained in the first lecture, well, in this case, the derivative has the meaning of the fraction of adsorbed monomers at the interface in the limit as n goes to infinity. So this number here for every zeta will give you precisely what the percentage is of monomers that are adsorbed on the interface. Because if you differentiate the partition sum, you get this thing down, and it counts the number of hits. And so you see that indeed the moment zeta starts to become positive, there is a positive fraction absorbed, and it will, as zeta becomes very large, go to the maximal value, which is a half. If I'm a simple random walk, the best I can do is sort of jump up and down and hit the interface every other time unit. Okay, so it's all really very simple and explicit. Now, what more can we do? You can get many more detailed results than the one the one I have told you about. And the reason for this is exactly that you have very strong control over the partition sum. This is a point that Francesco Caravena is also going to emphasize in the tutorial this afternoon. And this strong control allows you to get something much more detailed. For instance, if zeta is positive, then we have already seen that the interface is being hit at a strictly positive density, and this positive density was exactly equal to the derivative of f zeta. And you can prove things like the length and the height of the largest excursion that you will ever see away from the interface up to time n is of order log n. So if you look at how, so it will make these excursions, and when it's localized, it will come back with a positive frequency. And if you say, where is the largest excursion among all of them? And then the largest is of order log n, and both in length and in height. And you can describe this law into much greater detail as is done in the papers cited here. And if zeta is negative, then you can even prove that you will hit the interface finitely often. The free energy derivative will tell you that you will hit it at zero density, but you can even show that you will hit it finitely often. Your path will just say, okay, I hit it 5 or 6 times and I'm off. So it's really a finite number. And at zeta is equal to 0, well, then you are the non-interacting walk, and it depends on your excursion time distribution. It will be some power law. So you can get all of these things in great detail. Here's another result. And this is a result about the order of the phase transition. So you could say, well, what is happening close to this critical point, which is zeta equal to 0? How is the free energy behaving in the vicinity of this point? And you can prove in the following theorem, again in the general class of excursion distributions that you are putting here, where there's this exponent a, and a is a half in the case of simple random walk, but can be any positive number if you are looking at more general reference random walks. And you can show, and this will be the goal in a large part of the tutorial this afternoon by Francesco, that the free energy for very small zeta is scaling like a certain power law. And the power law depends on this exponent a. It's zeta to the power 1 over the minimum of a and 1. And then it's modulated by some slowly varying function that it has something to do with the slowly varying function that you put in here. But let's forget that for the moment. It's this power that plays a role. And therefore, you will find that if this power lies between 1 over m and 1 over m minus 1 for some integer m, then the order of the phase transition will be that number m. So it will be that. So then this number here will be exactly m. And so for the simple random walk, a is a half, and then you have to pick m is equal to 2. And that's in the picture that we drew for simple random walk, the behavior was quadratic near the origin. So here it's quadratic for simple random walk, but for other random walks, the behavior here will be some power law. And the exponent of that power law is what you call the order of the phase transition. And the order of the phase transition has the following intuitive meaning. The bigger the order is, the more smoothly the polymer comes off the interface when I increase zeta a little bit from 0. And if the order is low, then it sort of comes up more dramatically. So the order of the phase transition is a way of how it sort of gradually moves off the interface if I switch on a tiny little interaction. Okay. Let's go to the second version of the model, where I am going to make the following change. So part 2 will be the part where I do wetting. And all that changes is that I'm going to keep everything the same, but I'm going to add here that that I want things to live above the interface. So I do not allow my paths anymore to go below the interface, and otherwise everything is the same. So I make an innocent-looking change to the model, but that will, however, have interesting consequences. So this is the same definition as before, but I only allow my wi's, which is the height, to be on or above the interface and not below. So now the interface has become a kind of hard wall, and I can touch it, but I cannot go below it. Okay? And I'm adding this plus sign to make that distinction, so I should have added it here as well. And then I would have to add pluses here everywhere in order to remind you of that. Okay. The reference measure you can, doesn't matter because I'm not allowing any paths to do that. Yeah, so you would have to renormalize your partition sum to do that. Okay, so similar picture as before. I have a path with arbitrary increments. Doesn't have to be nearest neighbor. And it has to stay on one side of the interface. And here is an example of a 7-step path that hits twice the interface. The only difference is it has to lie on top of the interface. The rest of the model is completely the same. Now, just as before, the key object will be the excursion length distribution of your reference random walk. If I have a good enough understanding of how my reference random walk makes excursions, this time on one side of the interface, and I have good enough control of that. As Chuck said, it doesn't have to be a random walk. You could even make a more general path, but let's think of random walks here. Then if I have good enough control of that object, we saw that we could compute everything. So there is again, so here is the probability that you will make an excursion of length n on top of the interface. So it's here, different from 0 has now been replaced by strictly positive. So you're on top of the interface and you ask, what is the probability that you do a thing like this? So this thing now here is not possible, but you have to stay on one side of the interface. Again, you can introduce a generating function for that object. An important thing to note is that this is no longer a probability distribution. It is a defective probability distribution because the reference random walk will typically go below the interface. So this is still a distribution on the positive integers, but it doesn't sum up to 1. We have to take note of that. I can still put the generating function of these numbers here. And what I have to do is I have to normalize this quantity here to turn it into a probability distribution. So r plus 1 would be by what I would have to normalize it. So I would get, if I would divide this thing by this r plus 1, and this, I'm sorry for the notation, this is really the generating function variable, and this is the variable n here, so I should be using bars on top of that. Francesco uses a different notation for that, so that will be better. And then I have to normalize it, then I will get a normalized generating function. This will be the generating function of a probability distribution, and this normalizing factor, log of 1 over that normalizing factor, is what I would call zeta plus. And what then happens is that I have exactly the same theorem as before, except that the free energy now starts to become positive at this value zeta critical plus. So let me remind that here. So zeta critical plus is the logarithm of 1 over the sum over all n of r plus n. So 1 over the probability that my reference random walk is going to stay on one side of the interface before it returns to the interface. And there is nothing new under the sun. After you've done this normalization, I gave you a very simple argument. You just pull out a normalization factor, and then you redo the argument. And the upshot will be that you will now start to become positive beyond a non-trivial number, and this number will be strictly positive because this sum here is typically smaller than 1. For a random walk to make an excursion on one side will typically be having a probability smaller than 1. And again, everything is the same. You just have to shift everything by zeta plus and solve a similar equation as before, and that will give you the free energy. So there's very little change. The difference is that now this free energy, so let me draw a picture of that. Now the free energy simply comes up at a different value. So there's here this zeta critical plus, and the free energy starts to become positive here rather than at 0. Now, and that is something that is intuitively quite obvious, because when you want to hit this interface, but you're only allowed to do it from one side, then going to the interface is a difficult thing to do, because there's entropic repulsion. You can go to the interface, but you have to stay on one side, so by going to the interface, you lose a lot of paths that can do this easily. And that is a cost that you have to overcome. And it is that cost that will causes you to have to make the reward substantial enough for this polymer to want to localize near the interface, because it has to, it doesn't like to do that because it has to stay on one side of the wall. Okay, so things are very similar, and in the case of simple random walk, there is even a very direct relation, because simple random walk, then the probability that you will return to the interface, you have two possibilities. You can either do it on top or on bottom, because you cannot cross the interface, you cannot jump over the interface. And so for the simple random walk, the one-sided return probability is just a half times the two-sided return probability, and therefore the whole distribution R plus is simply a half times the distribution of R. This normalization number becomes log 2, because these things sum up to a half. And sorry, this B should be an R. So that means that the normalized generating functions are the same, and therefore the free energy for the simple random walk in the wetting case is just a shift of the free energy in the pinning case. So in that particular case, there's a very simple relation. It just means that the whole free energy curve is being shifted to the right by log 2. If I allow for more general random walks than simple random walk, the relation is not as simple as this, but everything is still in terms of generating functions, and you can do everything that you like. And it will still be a picture of this type, etc., etc. Okay. So I have talked about the pin version, the two-sided version, and the wetting version, the one-sided version of interacting with an interface. And see that computations can be done explicitly. They're very simple. They're all in terms of renewal theory, excursions, and so all the fine details come out of being able to do renewal theory. In the third and the last topic of this lecture, I'm going to ask the question, what happens when you apply a force to the endpoint of a polymer that is absorbed? And it could be absorbed in the pinning version or the wetting version, and I'll write down some formulas in the pinning version, but the wetting version will be very similar. Now, how would you do this in practice? How can you pull on a polymer? Well, there's a device which is called optical tweezers, and this is a very, very important device in when you want to do experiments with polymers. And I thought it was sort of nice. You know, it's true that most of the time reality is there to inspire good theories, but occasionally it's fun to tell you about reality. So let's spend 2 minutes on that. How do optical tweezers work? Well, an optical tweezer, so tweezer, if you, maybe not all of you know this name, it's this little thing that you can, this fork that you can press and you can pick up a little thing from the table, or maybe pull something out of your nose. But you do this in an optical way. So it's something to do a very, very delicate operation. So if you take a laser beam, you can make the laser beam very focused, and the focused region of the beam is what you would call the beam waist. Okay? And in this beam waist, there is going to be a very strong electric field pointing to the center. Okay? Now, suppose I would sort of chemically attach a particle that is susceptible to feeling this electric field to the end of a polymer. So there are ways to do that chemically, to attach at the end of a polymer some dielectric particle. Then you can come with this beam and you can sort of put it in the neighborhood of this particle and start to pull on it. This particle wants to stay to the center of the beam because there's a strong gradient to the center, and so if I move the beam, the particle will want to stay in the middle of it, and I can sort of start to, with the help of my laser, to pull on this particle. And in current experiments, you can apply forces as small as 10 to the minus 12 Newton. So this can be done very, very precisely. For instance, the binding energies per base pair in a DNA molecule are of the order 10, 15, 20 piconewtons. So it's really in this range where you can start to manipulate this. And this is an absolutely amazing device with which you can study all sorts of structural properties of polymer chains. So isn't that fun that we can think about that for a second? Okay, so what are we going to do? We're going to use that device to pull on the polymer. So So here I'm having my interface, and I'm having my polymer sort of hitting the interface a couple of times. And then at the end point, I can apply a force that goes in the upward direction. And how would I have to modify my Hamiltonian to deal with that? Well, we already saw something similar at the end of the second lecture. I keep my Hamiltonian to be, the interaction with the interface is going to be the same as before. The Hamiltonian is going to be minus zeta times the local time of the path at the interface. But I'm adding a term which is this minus this force 5 points in the upward directions, times Wn. And why is this term appearing? Phi times Wn is the work that is exerted by the force to move the endpoint at a distance Wn from the interface. And so this work, is, since it's done by the force, it's being taken away from the polymer, and therefore it gets this negative energy. And so there's now the zeta parameter that we had before, but there's also a parameter phi that shows the strength of this force. And the question we will be addressing is, if you give me a zeta, for what forces will it be the case that I am able to pull off the polymer from the interface? So if I would take a zeta that would be positive, without the force, the thing wants to be close to the interface, as we saw, how big would I have to make phi so that I'm sort of really ripping it off the interface? And this should be, one should be able to find that by looking at the free energy associated with this Hamiltonian. So this is the Hamiltonian, this is the partition sum in the Gibbs path measure that you get by using this Hamiltonian, and I will stick to the same reference random walk. I'm not changing that at all. In fact, I will soon make a particular choice for that for the calculation. And if we should be able to see a phase transition in this thing should have different behavior when phi is small and when phi is large, and there should be some sort of crossover. So can we compute that? Well, of course we can, because the model is very simple, and let's see how you would try and do that. Okay, to do that computation, I'm going to now make the reference random walk a bit simpler. I will only allow it to make increments of size 0, -1, and +1. And I will make the jumps, the increments of size -1 and +1, equal probability, both a half p, and the probability to make an increment 0, 1 minus p. And p is a parameter I can play with, and if p is 1, then this will disappear and you get simple random walk. And if p is 2/3, all 3 steps are equally probability. And this is a class of reference random walks that I want to look at. And no surprise that you can compute things again explicitly, and here is what things look like. For every choice of parameter zeta and a positive phi, I'm going to take phi positive here because I want to look at doing a computation where it's being pulled in the positive direction. The free energy of the polymer with force is the maximum of 2 things. It is the old free energy, where there was no force present, and a function that only depends on the force. So this thing you can think of as the free energy of the polymer when I have the force present, but I completely switch off the interaction. And this function is very simple to compute, and it's given by this simple functional here, where the phi appears and the p appears. So the free energy is the maximum of 2 possible things. One that depends on zeta and one thing that depends on phi. And I want to do the computation that gives this. The first thing I do is I say, well, let's write my partition sum in yeah, sure. There are other formulations of this model. Yeah. So in this picture, I can say, well, where was the last hit, which would be n minus m? And here's n. So, and here's 0. I can decompose my partition sum according to a distribution. I look at all paths that hit the interface at time n minus m, and then there will be a piece at which it no longer hits the interface and ends at a certain value x. So this part of the partition sum applies to the last piece over there, where you say in the last m steps, I leave the interface, I end at height x, and if I'm at height x, in my partition sum, this force term will give me a contribution e to the phi of x. And so this part of the contribution to the partition sum is given by this functional that only depends on phi. It doesn't, this piece of the path doesn't hit the interface, so it doesn't depend on zeta. And then I have this renewal equation saying, well, I can sum over all times that I was at the interface for the last time, and therefore that is why there are two zeros here. This is the case where m is equal to 0, because that is the path, that's the partition sum constrained to end at the interface. Okay, now, then because of this, we know the growth rate of this thing. It grows like e to the n times f. This also grows like e to the n minus m times f. So if we know the growth rate of this object, we will be done. And in fact, all that we need to know is that the growth rate of this thing here is this function g that I have here, because if I know that, then the growth rate of this thing will be the maximum of the growth rate of this thing and the growth rate of that thing. Right? And this sum is so simple that the growth rate will be determined by the maximal growth rate, because the total length of the sum is just is of order n. And indeed, that was what we were trying to prove, that the free energy was the maximum of the growth rate of the partition sum without force and this extra term. So let's look at what this thing is. So all our goal is to get the growth rate of that object. And this object was a simple sum. It was the sum over all x. So let me put that up again. It was this simple sum where you say this is the probability that the walk leaves the interface, doesn't come back up to time n, and manages to reach height x. And these probabilities, we want to compute essentially the moment generating function of these probabilities. Now, the first thing I'm going to say is the phi is positive, so contributions coming from the negative values of x are going to be negligible, because these numbers are smaller than or at most 1, and therefore, since phi is positive, the contribution of this sum for negative x is just some finite number, and that can never contribute to the growth rate of this object here. So we really only need to worry about the positive part of this sum. Okay, so that is what I'm saying. The negative part of the sum, the contribution, can be bounded by a finite number, and it doesn't play any role. Let's take positive values of x. Well, the thing that we're going to use is that this probability that you stay on one side of the interface and manage to hit the point x, you can use a reflection principle, and it's important now that the increments can never be larger than 1. You can use a reflection principle to relate, to give that probability, to write it as a difference of the unconstrained path probability. So this is the probability that at time m minus 1 I will be below x and above x in the unconstrained walk, so the walk not forced to stay on one side of the interface. And this difference times p over 2 is exactly equal to the constrained probability that I end at x. So this is a very simple symmetry property that I can apply for this nearest neighbor random walk. And if I substitute that, then I can get a nicer expression for this in terms of unconstrained probabilities. Here is the term that came from the negative values of x, which is order 1. And if I substitute, so I had an e to the phi x, and I had here this constrained probability. If I substitute that that's a difference of two things, I can sort of rearrange the sum, and I will get only one term here, and there is, by basically shifting the sums, I get a very simple function of sine hyperbolic. So this is something, if you sit down for a second, you'll see it immediately. Now again, I can re-extend this sum to z, saying again that this would be exponentially decaying. This is still a number smaller than 1, so there I would pay another time a price that is of order 1 negligible, and I can then extend this thing to the full sum. And this is just the moment generating function of s of n minus 1, of the unconstrained random walk. And that's a very simple object because the unconstrained random walk makes independent increments. So here actually, Chuck, it is important that we're talking about a random walk. And this is very, you can compute this explicitly, and if you stick everything in, you will see that the growth rate of this object is exactly the logarithm of this object here, which was the one that was in the theorem. So what does this lead to? This leads to the following situation. This free energy is the maximum of two terms, the free energy without force and the free energy without interaction. And so there are two regimes. The regime, one is the regime where the free energy without force is larger than the free energy without interaction. And the other case is when it's just exactly the way around. And in this case, it should be that the interaction is winning and you should be absorbed still at the interface. Your force is not large enough to pull you away or to have really any effect at the level of the free energy. And in this opposite case, it is apparently the force that is winning, and it should correspond to the force being able to pull you off the interface. And the critical value of the force is given by this function. You take the free energy of the model without force, you stick that into the inverse of the function g that we found, which was this log of cosine, and then you will be able to find what the critical force is. Now this is not such a very simple function. This inverse function is not terribly simple, but of course you can get all the qualitative behavior out of it that you want. And I want to now discuss, I want to discuss this relation a bit. We know that this is now the critical curve, and I want to show, well, what does this thing actually look like now? I mean, we have a formula, and can we get the qualitative properties out of this thing? And yes, I'm going to do that now. And I have 5 minutes left, and I will manage to do things there. In order to make this a bit more appealing, I'm going to switch now to parameters that really have a physical language. So the z was an interaction strength, and I want to think of it as the inverse temperature. So I'm replacing z now by 1 over the temperature. Right? Always large temperature means weak interaction, small temperature means strong interaction. And so this is we're going to reparameterize this like this. The force, I'm also going to scale everything by the temperature. So the force in the temperature force units will be F over T, right? So I'm having a new parameterization of my force, which I will call F. And then the critical force that we are after should be this phi critical that I had at the previous slide at zeta is now 1 over T divided by T because there's a T over here. And what we're going to do is to plot the critical curve as a function of the temperature. And it will turn out that this has an interesting behavior. And remember that we were allowing jumps that were the jumps of this size plus 1 had a probability P over 2, minus 1 had a probability P over 2, and jumps 0 had a probability 1 minus P. And it turns out that this curve has qualitatively different behavior whether P is small or large. And there's a crossover at P is 2/3, and P is 2/3 is exactly when all three jumps have equal probability. So let me show you what is happening if P is between 2/3 and 1. It then turns out that the force as a function of temperature is going through a minimum. If P is below 2/3, it will not go through a minimum, it will go up like that. The minimum pops up only when P is between 2/3 and 1. So it means that the motion along the interface is becoming unlikely. And the fact that this goes through a minimum is really something sort of that surprises you at the beginning. You say, how is it possible that if the temperature is very low, I need to pull on it, I increase the temperature and I need to pull on it less, and then if I increase the temperature further, I need to pull on it even more. So why are things not monotone in the temperature? And I'm going to attempt an explanation of this, but I'm going to fail miserably to really convey the message because it's really something that you have to think about. And so I wrote down a few things. Let me cut this short and perhaps you read it in the notes. Or I've expanded much more on this in the Saint Flour lectures that I gave. Basically, what happens is if this polymer is absorbed, it still has some residual entropy. It still wiggles around the interface. It's not flat on the interface, and it still has some sort of entropy. And this entropy, the moment I start to pull on the polymer, I make the endpoints sort of go up very steep, and so then this polymer is going to lose some of this entropy. Because I force it to sort of go up, and I'm taking away some of its entropy. And this entropy has to be counterbalanced by the force, and the free energy is energy minus temperature times entropy, and so the entropy and the temperature play a very important role. The temperature plays an important role in the competition between energy and entropy. Entropy just means there are many paths that can do it or few paths that can do it. And there is some balance between these two, and this balance is all controlled by the temperature. You will really only appreciate this if you are familiar with equilibrium statistical mechanics. And therefore, there is something really subtle going on, and the way this is subtle will depend on how much entropy the path has when it is absorbed, and this is very much controlled by this parameter P. So there is this remarkable thing that the force can sometimes be a non-monotone function of the temperature. And this is called a re-entrant phase transition. Sometimes it occurs, sometimes it does not occur, and it is something a bit subtle and also interesting. So it's time for me to wrap up. We have been looking, so I'm always giving you a kind of take-home message. We've been looking at this polymer close to a homogeneous interface. The interface was flat. It was a very simple model. We could do calculations in terms of excursions, of random walks. And there were two versions, a pinning version where the polymer could live on both sides of the interface, and a wetting version where it could live on one side of the interface. And the message was we could do many things because of the simple structure of the calculation. Now, there is a whole area that moves beyond the simple interface where you say, well, what happens when this interface is, there's not just one interface, but there would be some kind of slab, and the polymer has to live between two walls. This is a very interesting thing because it's used to model what are called colloidal dispersions. So you can take micro droplets, you can stick polymers onto it, and then these polymers can either help or prevent the droplets from coagulating. For instance, if you take paint, it is very important that the droplets in paint are coated with the polymer, because before once you take the paint out of the pot, you don't want the paint to sort of, the droplets to condense. But if you've put it on your wall, you wouldn't like the paint to sort of drip off the wall. You want it to stick. So the moment you paint and air comes to it, you will see that there is something happening, and this is exactly because of polymer chains sort of attaching to interfaces of droplets. So this area is for that thing very important. Now, there are many more interesting things that you can do, and in fact, this is also related to something that Philippe Di Francesco in week 2 spoke about in his first lecture, that there is a whole combinatorics of counting paths close to interfaces, and there's here I've listed a bunch of people who have worked on this, and this list is really, really very, very long. So let me close up here by saying that at the end of the third tutorial, Francesco will very briefly mention some of this extension, in particular when you have a whole array of interfaces, so he will come to that. Thank you very much.
Questions?
Tatjana.